Alright, for the section 5 and 5, we finally get to the formula for counting that are pretty common. That we have a name for that, and we use it a lot. So let's do permutation and combination. First of all, the names don't make sense too much, so don't worry about the names, but you still have to, remember the names of the permutations and combination. Yeah, these are two different things that have similar formulas, similar wordings, but the way you solve it and the way you solve them and the way you write the formulas are different. So let's start from the permutation. The permutation is the definition is simply a possible ordered selections of R objects of a total of n objects. So at this point it sounds nonsense. Yeah, there should be at least some kind of image that I forgot to add. So there are two variables here. First we have n objects. And usually you can think of n people or n balls or n cards. Let's say there are four cards at first, and you want to select R of them. Let's say you want to select and order 3 of them. Maybe you select 3 as the first one, and then 4, and then 3. Oh, and then 2. Sorry. This result is a permutation. So from, maybe I shouldn't write them as in order. Let's say that there are 4 balls on the table. You select 3 of them in order. So 3 is the first ball, is on the leftmost one. 4 is the second ball, is in the middle one, and then 2 is the rightmost one, the third one. This result, 3, 4, 1, is a permutation of these 4 numbers. As simple as that, but maybe we need some extra example to understand the definition. So for instance, how many permutations are there of letters ABC? And one thing I forgot to mention earlier is that if R is not mentioned, if R is not mentioned, right, then we can assume that R and N are the same. Or in this case, you permute. You find the permutation of all objects. Like for instance, in example 5, we ask for permutations of these 3 letters, but we don't mention how many objects we choose. So that means we choose all of them. We permute all of those numbers. So in this case, if you want to get just the numbers out, n is 3, there are 3 objects to permute, and I is 3 also, because i's are not included, so we permute all of them. So at first, just we have to do it by hand, because again, there is no formula at all. How do we permute them? There are 2 ways. First, you can just do it by hand and hope you don't mess up. So you can do ABC, you can do BCA, ABCAB, maybe BAC, maybe ABC, and then ACB, and then CBA. Wait a minute. How many are there? 7? Are there 7 permutations? No, because that was intention. Yeah, ABC should not appear twice, because we count different permutations. So the answer should be 6. So that's one way you can perform this task. Another way is to use the tool that we have already, which is a tree diagram. So with permutation of 3 objects, like it's the same. You can describe this procedure as selecting the first letter, selecting a letter to put in the first position, then selecting the second letter to put in the second position, and then select the third letter to put in the last position. So the first position can be anything. There is no restriction at all. So you can put A or B or C. If you choose A already, then the second position can be either B or C. You cannot select the same letter because we permute, and we just switch things. We think of them as physical objects, so you cannot duplicate the object itself. If you choose B, you can then select A or C to put in the second position. And lastly, if you put C first, then the second position can be either A or B. And once you have two letters, then actually the last position is fixed. If you choose A and then B, then there's only one letter left to be picked, which is C. If you choose A and C, then the last one must be B. If you choose B and then A, the last one must be C. And so on and so forth. And then you can see that these are all the possible ways to choose letters. And each of the leaf may correspond to a different permutation. The first leaf, like the topmost, comes from A and then B and then C. So it's the sequence A, B, C. It's the permutation A, B, C. Next one corresponds to A and then C and then B. So it's A, C, B. And you repeat that for all other permutations. That should give you all 6 permutations. And it should give you some kind of a guarantee that you get all of them. You are not missing anything. So that's the second method. We can use a tree diagram. And by the tree diagram, you can see that the number of permutations for this example is 3 times 2, because of each of the first branch have 2 other branches, and then each of the second branch has only 1 leaf, so it's 3 times 2 times 1, and 1 leaf. That's 3 branches. Each branch has 2 branches, and then each of the second branch has 1 leaf. And so the number of permutation is exactly 6. Which you can see that, that actually looks like a notation that we justify. And of course it is exactly 3 factorials. So that's how you can find the permutations of all these letters. The third way is, of course, you choose formula, but we didn't have it yet. But just to give you an idea of the formula, the formula is P of N and R. You will see the formula in a moment. N is 3. There are 3 letters to choose from, and we choose all 3 to arrange or to permute. So it's P 3 for this example. Okay, let's see next one. And by the way, it's going to be 6. So that's how you find permutations. Next, let's see another one. So suppose there are 4 letters to choose from, and you want to permute 2. You want to choose 2 of them, but in order. The first one, and then the second one. So again, you can do it by hand. Maybe AB, maybe AC, CB, BD, and so on and so forth. But if the numbers are getting larger, it is easier to make a mistake. So the second method, which is better, is to use some tool. In this case, we can use the tree diagram. The first letter, like in the first position, there are 4 options to choose from. And so that's 4. And then after you choose a letter to put in the first position, the next letter must be different, because it is a permutation. You choose from physical objects on the table to arrange, to put together. Okay, so if you choose A, you have 3 options left, B, C, D. If you choose C, you have 3 options left, B, C, A, C, or D. If you choose C, you get 3 options left, A, B, or D. And lastly, if you choose D, you have A, B, or C. And each of these branch has 3 leaves. And so the answer for this one is 4 times 3, which is 12. So at the end, there should be 12 permutations. And if you do it here, then you should get all. If you look at the leaf and walk through the branches, then you should get all the permutations. So in this case, you get AB, that's AC, that's AD, and then you get BA, and then BC, and then BD, and then dA, and then dB, and then dC. Oh, that should be C. And oh, my bad. That was C. So it should be CA, and then CB, and then CD, and lastly it should be DA, DB, and DC. So hopefully we get all 12 permutations. And lastly, of course, we can use the formula. We will see in a moment that n is 4. There are four letters or 4 objects to choose from, and you permute 2 letters at a time. So it's 4p4 true. And if you use the formula correctly, you should get 12 as well. So that's a permutation. And that's a first example. Second example, right? And there's this example also, but let me skip to the formula. You can see from these 2 examples that they have similar computation. You start from choosing any one object. If there are 3, you choose any of those 3. If there are 4 objects, you choose any of those 4. Okay, so the formula should be something like as follows. Like the first arrangement, like all the leftmost object, like that should be n. Or if there are n objects, 1, 2, 3, all the way up to n. Like in the first position, there should be n objects to choose from. Then there should be 1 fewer objects because you cannot choose the same object, right? And any of these branch have the same number of objects, which is n-1. So by the rule of product, is n times n-1 for the second object, right? And this trend continues. For the third object, you cannot choose the first 2. Right? They are gone. You choose them already. Then that means there are only n-2 objects left to choose from, and that trend continues until the last one. And this is where people get confused, right? Because okay, how many objects do we need? We need to put R objects. So does it mean the last one is n-r? No. That's the problem of being off by 1. Because if you see the leftmost one, we didn't start from 1. If we start from 1, right, and do repeat this r times, then we would have n at r. If we start from 1, but we start from 0, right? We start at n-0. That's the first term. Right? That means if you want r objects, and if you start counting from 0, right, then they should end. It should end at r-1. It's off by 1. So you end at r-1. And in this case, you should have 1, 2, 3, also on so on up to r. Which you can also double check, right? And in the first one, n-0 is the first object is n-0. The second object is n-1. The third object is n-2, and so on until the r object should be r n-1. It's one number smaller than r. If you write it in this way, then this is the result you get. But if you see this one, some of you might be tempted to expand it, and maybe there's another problem about this. Because if you expand it, you should get n-r plus 1. It becomes plus 1 because it has minus and minus. You distribute that, get minus times minus 1, which is plus 1. So in the formula, you see that the last number is n-r plus 1. Where in fact, I think this makes more sense if you write it as n minus open parenthesis r-1 close parenthesis. So that's the proof of the formula. But that means, okay, now we have a general case. Like no matter how many objects we have, if we have n objects and we choose r object, right, the number of permutation is this product. The number of permutations is the product from n times n-1 times n-2 all the way down to n minus r minus 1. And that's a formula for permutation, which I think I should give you as as a formula on a page like that. So the number of permutations of an object. I should also add the distinct, but I assume they are distinct. And distinct objects taken r at a time. You can think of them as you arrange in a line. So that means you care better. You think you take the first, second, third, fourth. The order matters. And the answer is this formula. Alright, so let's try if we can apply that. In the next example, suppose there are 4 people to be chosen at random out of 10 people to be interviewed. Or maybe you don't have enough time to interview them all, so you only choose 4. How many ways? Usually you should say how many ways are there in general. But in this case, I add the word permutation, so to make it easier. But usually it's on you to look at the sentence, look at the statement, and see what kind of formulas or what kind of techniques we need to apply. And here we know that we need to apply permutations because first the objects are all distinct. The objects are all distinct. Why? Because they are people. Even if they are twins, we treat them as 2 distinct people. And second, the order matters. Because these 4 people need to be interviewed one at a time. Okay, the first one comes at 1 p.m., the next one at 2, the next one at 3, and the next one at 4. Now the order here matters. And maybe also there should be said somewhere that we don't ask them all to be in the same room at the same time as a group. We ask them to interview in 4 different slots. So based on these 2 requirements, then we know that we are dealing with the permutation. So the next question is, how many permutations are there? How many ways are there? How many permutations are there? And the answer is simply the formula. How many people or how many objects we have? We have 10 objects. We want to choose only 4 at a time. Oh, not 4 at a time. So that's the formula. Now, usually, if you write this way, then everyone should understand what you are trying to say. But in case you want a number, you can expand that. Then the first number is 10. And the first person to be interviewed can be chosen from any of the 10. Then the next person must be 9 of those 10. You don't interview the same person over and over again. That would be called like interrogation. But the next person, there are only 9 options. Then in the third slot, the third person to come in can be chosen from 8 remaining people. And lastly, we have 7. So there are 4 people. This might be easier to see. But if you apply the formula, then the formula should be 10 minus 4 plus 1. And so the last entry, the last number should be that, which is, of course, 7. And once you have that, then you just have to, do the math. It should give you 5,040. So there are 5,000 ways you can permute or you can arrange the interview for these 4 people. And that's the only permutation example. And there are some properties and there are some notes about this one. Like first, if you ask you to find P of n0, then there are 2 ways to accomplish that. You can plug that into the formula. The fascinating things about combinatorics is that you can solve the same problem in at least 2 different ways. You can use a formula, which I will give you, or you can use some kind of an argument for or definition. Use your reasoning to conclude, get the number you want. So if you use the formula, right, then just apply the formula. In this case, the formula will be weird because you multiply m all the way down to n minus r plus 1. What is r? R is 0. So you multiply n all the way to n plus 1. Doesn't make sense, right? If you go from n to m plus 1, you have to go up, not go down. So what's wrong here? What's wrong here is again similar to the 0 factorial formula. And because this may be one of the time when the formula doesn't make sense unless you use a different approach. And here the different approach is as follows. So suppose there are n objects. So there are n people, all the way up to n. Suppose there are n people in the room, and you are asked to select 0 people. How many ways you can select 0 people? Do you think it's 0? Or you think it's 1? How many ways are there? Yeah, it seems like it's 0, right? Oh yeah, 0, so it's 0. There is no way to select. But in fact, there is a way to select 0 people. Think about it. Can you select 0 people? Yes. You just give them back the blank, the empty list. Okay, list all the people you select. Here it is, a blank piece of paper. Yeah, so indeed there is a way to permute 0 people, which is to do nothing. And again, it goes back to the concept of if you multiply nothing, you get 1, not 0. And so that's why this is 1. So that's the first property. And the second one is the factorial formula. And so if you have n people and you have to arrange them all, right, then that's the same as you start from n and then pnn. Start from n and then multiply that by n minus 1, n minus 2, and so on all the way down to 3 to 1. If you do it correctly, then there should be n numbers. How many are there? 1, 2, 3, 4, 5, all the way up to n. So yeah, indeed there are exactly n terms to be multiplied. That's exactly n factorial. And so in a sense, you can think of a factorial as the number of ways to permute n objects. Maybe that makes more sense than the formula itself. Yeah, that's the number of ways to permute n objects. Or if there are n people in a row, if you ask how many ways you can switch them out, or you switch them around to form a row, then it should be n factorial. And lastly, we have a formula, in case you love formula. Because again, the formula here is not well defined. If you plug in I equal to 0, then everything breaks apart. And so there must be a better formula, which is this formula. How do we get this formula? If you go back to the formula for permutation, you can see that it starts from n and it stops at n minus r plus 1. What is the next number? If you go one step below this number, you should get n minus r. It is this number minus 1. You get to n minus r. And then n minus r minus 1. So on and so forth up to 1. Okay, so you can kind of fill in the gap of the rest of the sequence. But you cannot just multiply numbers randomly to get a new number. If you still want to keep the same formula, yeah, you can multiply numbers, but you have to also divide by the same number, so they cancel out, and you simply get a new number that has the same value, just in different form. And then if you ask what is the number at the top, at the top, in the numerator, we have n times n minus 1, all the way up to 1. We bridge the gap here and continue them all the way up to 1. So the top is n factorial. What about the bottom? We have n minus r. Like we start from n minus r all the way down to 1, so it's n minus r factorial. So it is the new formula, which shorter and also makes more sense. Right, we don't have to worry about wait, is it plus 1 or minus 1 anymore. Right, it's just r in this formula. And then you can cancel these two out. And also, another nice thing about this formula is that now it makes sense to plug in value r equals to 0. Because based on this formula, if you plug in r equals to 0, you would get n factorial divided by n minus 0 factorial. It gives you n factorial over n factorial, which is 1. So yeah, now we have a proof. We have a proof that if we select nothing, and then the number of ways to select nothing is 1. So that's the permutation.